In this lecture, we would discuss positive definite matrices and the minimum principle. So, we have already studied that every symmetric matrix has real eigenvalues. And here we will learn methods that will guarantee that all those eigenvalues are positive, which means that in order to say that a symmetric matrix has real eigenvalues, I need to calculate those eigenvalues and check and then say that these eigenvalues are positive. Whereas, so in this lecture, we would see that without calculating the eigenvalues, we can ensure that these eigenvalues are positive. So based on the three ideas, that is the pivots, determinants, and eigenvalues. And the signs of eigenvalues are very critical. For stability in differential equations, we need negative eigenvalues so that e to the power lambda t would decay. And the important problem through the data science, and engineering and every problem of optimization. So we have the problem of optimization, and the major goal is to find the minimum point in such problems. The mathematical problem is to move the second derivative test, that is the f double dash second derivative greater than 0 into the n dimensions. So now, given two equations, is capital F of x comma y equal to 7 plus 2 into x plus y whole square minus y sine y minus x cube is the equation. And on the other hand, I have small f x comma y equal to 2x square plus 4xy plus y square. This is another equation. Now I ask you a question, whether these two functions have minimum. Okay. So how can we solve this problem? How can we find the minimum point, and how can we ensure that there is a minimum in this function? So does f of x comma y or small f x comma y have a minimum at the point x comma y comma 0? So we will look into the techniques which will ensure that there is a minimum. So these two equations are already given in the previous slide, and now just let us just substitute f 0 comma 0 x comma y as 0 comma 0. So the zero order terms, that is f of 0 comma 0 in this case is 7, and f of 0 comma 0 in this equation it is 0 here. So have no effect on the answer. So this will not give me any clue that there is a minimum. So they simply, so what do they say? They say that they simply raise or lower the graph, that is the capital F, this graph and this another graph. And now the clue is that the linear terms give a necessary condition. So now we would try to look into that. To have any chance of minimum, the first derivative must vanish at x equal to y equal to 0. So this is a very important criteria, that given a function, we need to calculate the first derivative and substitute x equal to y equal to, that means substitute the derivative as 0 at the point x comma y comma 0. So now I will differentiate this function. I will partially differentiate, because we know that this function is made up of two variables. So now let me differentiate this capital F x comma y with respect to x, that is del f by del x equal to, okay, 4 into x plus y. So this becomes 0 because this is a constant, and now remaining is x term is here. So now what will happen is that this 2 will come here, 2 into 2 it will be 4 plus 4 into x plus y will remain here, and then this is all y, this is constant, and it will be 0 here. So similarly x cube will be differentiated as 3x square, and now when I substitute x and y 0, I get 0 here. Similarly, you can see that same function capital F x comma y, I would differentiate with respect to y, keeping x as constant. Del f by del y equal to 4 into x plus y minus y cos y minus y sin y equal to 0. You substitute x and y as 0, you will get 0 here. Similarly, del f, small f, del f by del x equal to 4x plus 4y equal to 0. So I have differentiated this with respect to x, keeping y as constant. I got 4x plus 4y. Similarly, del f by del y equal to 4x plus 2y is 0 here. Now we can see that the first derivative must vanish at x equal to y equal to 0. So that means that here x equal, we have substituted x and y, and we saw that derivative. Yeah, so this df by del f by del x is 0. Del f by del y yeah, is also 0. So thus x comma y equal to 0 comma 0 is a stationary point for both the functions. So this implies that it is a stationary point for both the functions 0 comma 0. The surface z equal to f of x comma y is a tangent to the horizontal plane z equal to 7. So z equal to 7 is the plane. And now the surface z equal to small f x comma y is a tangent to the plane at 0. So because this gives 0, this gives 7 when you substitute 0. So the plane here, the tangential plane will be z equal to 0 and z equal to 7 in this functions. So the question is now whether the graphs. So now in this case we have, by differentiating and by differentiating at the point x equal to y equal to 0, right, we have ensured that there is a minimum. And now there is a minimum point, but we don't know whether that is increase, means whether that is, the question is whether the graph goes above the plane or not. That means, so you have ensured that there is some point here. So let me take the color. Yes, so we have ensured that there is some minimum point, but we don't know, see, whether it is increasing, in one direction and decreasing in another direction, or whether it is increasing, or whether it is increasing in both the directions, right? It is increasing in both this direction as well as this direction, or it is in this direction, or it is moving. There is a point here, but whether this is decreasing in both the direction, so which we have not made sure. So now we will use second derivative to ensure that. So given functions f of these two functions, capital F of x comma y, small f x comma y, the second derivative test at x equal to x comma y equal to 0 comma 0 is very significant. And now let me differentiate this capital F. Okay, differentiating del 2f by del x square equal to 4 minus 6x. So now when I substitute x equal to y equal to 0, now you see that I get 4 here. That means the value is positive in this case. Similarly, I would differentiate del 2f by del x del y. Similarly, if you do in reverse way, del 2f del 2f by del y into del x equal to 4. So you get 4 in both the cases. Similarly, del 2f by del y square is equal to 4 plus y sine y minus 2 cos y. So if you substitute x equal to y equal to 0, right? So you get the 2 as the answer. Similarly, the other function, that is small f x comma y, del 2f by del x square, again it gives 4, del 2f by del x del y, del 2f by del y del x equal to 4. You get it again. Same case, same values you try to get. So now the finally del 2f by del y square also gives you 2. So what does this imply? So these two graphs, the second derivatives remain positive. So this implies that the graph, whatever the point you got at 0 comma 0 is a minimum point. The two, okay, it is a minimum point because the graph, the values, the points, the graph is moving in upward direction, okay, from the minimum. So that is the idea. The two functions behave in exactly the same way near the origin. F has a minimum if and only if small f has minimum. The higher degree term in f have no effect on the question of local minimum, but they can prevent it from being the global minimum. So now we know that the quadratic equation is usually represented as ax square plus 2bxy plus cy square. So every quadratic form has a stationary point at the origin where, okay, where del f by del x, del f by del y is equal to 0. So we know that at the origin, so these derivatives will be equal to 0. Okay, so that is what is here in this case. Okay, this is the minimum point, and we see that the function is, okay, the function is increasing in both the direction. So now a local minimum would be the global minimum in this case. The surface z equal to f of x comma y will then be shaped like a bowl. So you get in such a case, such a quadratic equation, you would get a bowl shape resting at the origin. And if the stationary point, now for example, this stationary point is at 0 comma 0. Now if the stationary point of f is at x equal to alpha, y equal to beta, somewhere above or somewhere below, so below the origin, the only change would be to use a second derivative. So we have used second derivative at 0 comma 0 in the previous slide. Now in such a case where the stationary point is above or below the origin, in such a case you need to use the second derivative at alpha comma beta, and the quadratic form can be represented like this. Okay, the quadratic form will be represented like this. Okay, so here, so I have just rearranged. You can see that this is the same thing. You can see that there is x square term here, there is a xy term here, there is a y square term here, right? So so here I have just represented this quadratic form by making use of the second derivative. So now in the coming slides we would see that what is the condition. Okay, what is the condition where we can ensure that the bowl, okay, whatever the graph you get, the function you get is increasing function, okay, in both the direction. So now let us consider this graph, which is f equal to x square plus y square, and we know that this is a very beautiful graph where minimum is at the point 0 comma 0, x and y 0 comma 0, and the graph is moving. Okay, the graph is increasing in both the directions. Okay, the graph is moving up in both the directions. And now, so this is a very beautiful graph where the minimum can be located. Okay, so it is a very bowl shape, and minimum is guaranteed at this particular graph. Whereas in this case, if you see, okay, the minimum point, though it is at the point this at 0 comma 0, but this is not a bowl shape, this is a saddle point. So why it is saddle? Because in this direction the graph is moving up, in this direction the graph is moving up, but on the other hand the graph is moving in negative, decreasing in another direction, similarly the other way, right? So this is a saddle point because we are not sure that this is the minimum point. So such a point is called, such a graph is called the saddle graph, where the points are increasing in one means the graph is increasing in one direction and decreasing in another direction. So it creates a problem. Though the third derivative are drawn into the problem when the second derivative fails to definite decision. We are unable to make any decision. This happens when the quadratic part is singular. For a true minimum, f is allowed to vanish only at x equal to y equal to 0. So for a true minimum, you would definitely get the clue at x equal to y equal to 0 about the minimum. When fx comma y is strictly positive at all other points, the bowl goes up. So f of x comma y in this graph, you can see that f of x comma y is strictly positive at all points, and in such a case you get a bowl that goes up, and it is called positive definite. So now in this case, the matrix which is generated will be the positive definite. Okay, positive definite matrix. We'll see in the coming slides. So definite versus indefinite, bowl versus saddle. So now given a quadratic equation f of x comma y is equal to ax square plus 2bxy plus cy square, what is the condition on A, B, and C to ensure that the graph is positive definite? Means the graph is increasing, like in this case the graph is strictly positive at all points, right, at all x values. So that is the key idea here. Now for that, what is the on the other hand, we have already calculated second derivative and we have ensured that the condition that second derivative should be greater than 0. Second derivative should be positive. For a function with two variables, what is the correct replacement for this particular condition? We want to ensure that. Now we have three derivatives, right? Second derivative with respect to x and x, right? And with respect to x and y, y and x, and y. So these are the derivatives. So the condition now boils down to, if ax square plus 2bxy plus cy square is a positive definite, then what happens? Then necessarily a is greater than 0. So our first condition is that if it has to be positive definite, then this a value should be positive. Similarly, the second condition is that the c value, the variable c should be greater than 0. And finally, if this whole equation has to be a positive, then AC should be greater than B square. Okay, so now simply A is here, B is here, C is here, simply substitute here. AC should be, if it satisfies that AC greater than B square, then this is a positive definite. Okay, the graph is positive definite. Now let us see what is the test for minimum. Now we have seen that ax square plus 2bxy plus cy square is positive definite if and only if a is greater than 0 and ac is greater than b square. Now any graph that is capital F x comma y has a minimum at the point where, so now this is del f by del x equal to del f by del y equal to 0 with second derivative with respect to x is greater than 0, and second derivative of f with respect to x, right, del square f by del x square multiplied by del 2 f by del y square should be greater than del 2 f by del x del y whole square. So this is the condition. Okay, this is the condition by taking the derivatives. And now test for minimum. Since f has maximum, whenever minus f has minimum, we just reverse the sign of ABC. And actually AC is greater than B, AC greater than B square remains unchanged. The quadratic form is negative definite if and only if A is less than 0 and AC is greater than B square. The same change applies to maximum f x comma y. So now what will happen? Okay, what will happen when we have seen that AC should be greater than B square. Okay, AC should be greater than B square in the previous slide. And now in this, if AC is equal to B square in the quadratic equation, then we get such a case is called the singular case. And we get positive semi-definite. Okay, please remember the word. This is semi-definite when A is greater than 0. We get negative semi-definite when A is less than 0. And the prefix semi allows the possibility that f can be equal to 0 as it will be at the point x equal to b and y. If you substitute this point here, right, in this at this point, you can see in the equation you would get AC equal to b square. And now the surface z equal to f of x comma y degenerates a bowl into a valley. So now what will happen in such a case where AC equal to b square, the bowl which was the bowl shape, it will now get converted into a valley. It will get converted into a valley. The bowl shape will not remain as bowl, but it will get converted into a valley. Okay, so it will be valley like this. Okay, so it will be valley like this. Okay, hope you can imagine. I will show the graph at the end of this lecture. So now on the other hand, if AC is less than B square, what would happen? It happens when B dominates A and C. Okay, here if B dominates A and C, then we get the saddle point. And it also occurs if A and C have the opposite sign. So this is another condition. The two directions give opposite results, one direction f increases, in the other it decreases. We have already seen the diagram for the saddle point. Okay, so now so far we have seen the calculus way of ensuring that the graph is positive definite, right? So now let us see the linear algebra way to define positive definite matrices. So here whatever we do, we try to come up with a equation, right? We come up with a matrix here, matrix A, and we ensure that the matrix is positive definite matrix. The second derivative fits. So now let us see how can we convert a quadratic equation in the matrix form. The second derivative fits into a symmetric matrix. So now the terms ax square and cy square appear on the diagram. I will show you this one. The cross derivative 2bx xy is split between the same entry b above and below. Okay, above and below. I would just show you how it can be represented. So the quadratic form f of x comma y comes directly from a symmetric matrix 2 by 2. Okay, and so now given a matrix A, in order to convert into quadratic, simply what I do is that this is not R, this is R2. Okay, this is R2 and x transpose. So simply given a matrix, I multiply with x transpose on the left side and x on the right side. So I get it. So you can see here what I was talking about. So the terms ax square, that a will go on the principal diagonal first element here, and cy square will go here, c will go here, and 2bxy will be split into, okay, split into here in this on the other diagonal. Okay, so split between same entry b above and below. So this is the b value, and now you can see that x and y were the coordinates. So x and y is here, x and y is here. Now if you multiply this one, you would get the quadratic equation. It generalizes immediately into, so now the idea is that now we should be able to use this particular formula in n dimensions. So it is a perfect shorthand notation. Because I'm dealing with this matrix here, it would be easy for me to study the maxima and minima. For any symmetric matrix A, the product, that is x transpose AX, is a pure quadratic form f of x comma up to n xn, that is n variables. So now this is also Rn. Please remember, this is Rn, not this Rn continuously. It is R power n. So x transpose AX in E is in R power n, and the matrix would generalize. So this matrix will get generalized in this form, okay, in n dimensions. So now just to okay, so here the terms, the okay, the quadratic terms are here, and okay, here, and these are the coefficients with respect to that equation. So now given a equation that is f equal to 2x square plus 4xy plus y square. Now let us try to represent this. A, let us put it here, and b, let us put it, that is 1, put it here. Sorry, a and c, this is c, this is 2 and 1 is a and c. What is b? Therefore 2b is equal to 4. So b is 2. B is 2 in this case. So I substitute b here and I b here. I get a saddle point. So how do I say that this is saddle point? This is, so one way of saying that there is saddle point is that I try to calculate the determinant. So what is the determinant of 1 cross 1 matrix in this? That is a 2. So 2 is a positive number. Similarly, you take the determinant with respect to 1 into 1, determinant with respect to 2 into 2 matrix. So now when you take determinant with respect to 2 into 2 matrix here, now you see that 2 into 1 is 2, okay, minus 2 into 2, 4. So 2 minus 4, answer is negative. So one condition to say that it is a positive definite matrix is that the determinants, okay, all the determinants in terms of 1 into 1, 2 into 2 goes up to n into n, okay. So all the determinants from the left side calculated, it should be positive. So if it is not positive, then maybe there is a chance of saddle point, right? And it is, but it will not have, but it will not be positive. It will not have minimum, that is positive definite. Similarly, if you take the equation f equal to 2xy and in such a case, there is no a term and there is no c term. So you put 0, 0 here, and what is 2b? 2b is 2, so b is 1 and 1. Okay, so we can see that we got here, again we see that again the same way when you try to calculate determinant with respect to this one, right? So determinant is 0 here, so the condition fails because it is not positive, it is equal to 0, so there exists a saddle point. Similarly, you can go up to this one, but once the condition is not satisfied here, then we need not move forward. But you can see here 0 into 0, so answer is -1. Again, -1 is in this case is negative, and so there is this is not a positive definite. Whereas if you see this equation, that is this equation, when you try to see, okay, and now x1, x2, x3 are the three terms, okay, three associated with this equation, and I substitute the values here, okay, at this matrix, and now I'm saying that this has a minimum at this point. This is just to say that, so I would just use that condition. Okay, now this is 2. So there are many conditions, but I am using the determinant condition in this case. So 1 into 1 matrix out of this matrix is 2. So 2 is positive. So it is good. So now let us go for 2 into 2. Let us go for 2 into 2. 2 into 2 into 2 is 4. 4 minus into minus is minus, so it is 4 minus 1, the answer is 3. So this is also positive determinant. Similarly, now calculate determinant for this one. So now if you try to calculate again, this will be the positive. So I am telling that this matrix which is given, this matrix A is positive definite, and also this satisfied the other conditions which I am going to explain in the coming slides. Okay, what are those conditions? So it satisfies all the conditions of a positive definite, and hence I can say that the minimum exists at 0, 0. So f has minimum where the pure quadratic, okay, when the pure quadratic x transpose ax is positive definite. So I should ensure that the matrix A is positive definite, then only I can say that there exists a minimum. So now coming to the condition, right? Coming to the condition for positive definiteness, following test is a necessary and sufficient condition for real matrix A to be positive definite. So the first condition is that when you try, given a matrix A, you multiply with x transpose on the left side and or x on the right side, so that should be greater than 0 for all the non-zero real vectors of x. To substitute any x, that should be greater than 0. So this happens in the bowl case, right? So I have already shown that whatever the value of x you substitute, it will be positive. So this is the test number 1. What is the test number 2? In such a case, what will happen? All the eigenvalues of A satisfy lambda I greater than 0. So all the eigenvalues, if it is positive definite, then all the eigenvalues you can just calculate and just you can check whether all the eigenvalues are positive. And as I have shown in the previous slide, all the upper left submatrices, okay, ranging from 1 into 1, 2 into 2, okay, 3 into 3, and so on, moving up to n into n. So all submatrices, okay, upper left submatrices AK have positive determinant. That's what I tried to do in the previous slide. And all the pivots without row exchanges satisfy dk greater than 0. So to just explain you, so you get pivots when you do LU factorization, right? So now what happens is that given a matrix, right? Given a matrix, you see that you try to eliminate and you get it, right? You make it 0 on the lower side, and all these are, so now every diagonal element, you can see that all the diagonal A11, A22, A33, A44, these are all pivot elements. So all the pivots without row exchanges satisfy that dk greater than 0, means dk is the now pivots. All pivots should be positive. So here all the determinant should be positive in this case. In this case, all the pivot elements should be positive. So this is the necessary and sufficient condition for positive definite. So all these 4 conditions should be satisfied. So in the previous slide, I had shown you that this matrix, and now I'll just erase this one just to make it clear. Okay. Yes. So this matrix I showed you in the previous slide. If you try to check these conditions, right? If you try to check these conditions, you would see that all the properties, 4 properties, will be satisfied this matrix. Hence, this matrix is a positive definite matrix. Now, given 2 variables, that is x1 and x2, let us calculate what is x transpose Ax. Let us try to get the quadratic form. So, given a matrix A, 4 0 0 3, right? So it is given. So let us calculate what is the quadratic equation. So simply multiply x transpose A1 into x. So this is how it goes: x1 x2 matrix A followed by x1 x2, and now you get x1 x2, and you multiplied this one, you got 4x1 3x2. Again multiply, you will get 4x1 square plus 3x2 x1 square plus 3x2 square. So now here you see that there is a term, there is a c term, but there is no b term, right? There is no b term. So now a is 4, so a went here. What is c? C went 3 went here, but b is 0 and b is 0. So I got the matrix A. I got the quadratic equation and I got the respective matrix A. Similarly, let us have another matrix and try to calculate the quadratic equation. So I try to multiply x transpose A to x. I get it like this, and I try to simplify this, and you will get 3x1 square minus 2x1 x2 minus 2x1 x2, and then 7x2 square. So this gets simplified. Now let us try to put this in the equation form, in the matrix form. What is A in this case? In this A is 3, and what is C? The C is 7, and what is B? So 2B equal to minus 4, and so B equal to minus 2. So minus 2 will go here, and minus 2 will come here. Okay, so this is the quadratic form, right? So now let us come to the minimum principle. So the minimum principle is a very interesting concept in machine learning or in any optimization problems. The heavy liquids sink to the bottom is a consequence of minimizing their potential energy. Okay, so this happens, right? So when you have a when you have a bowl shaped object, and then when you try to put something in that, so it will directly go and it will try to minimize its energy and be at the minimum point, that is at the center point there. So when you sit on a chair, sleep on a bed, the springs adjust themselves so that energy is minimized. These energies are nothing but positive definite quadratic functions. So we must understand that what are these energies? These energies are as good as positive definite quadratic functions. So the derivative of a quadratic is a linear. We already know derivative of a quadratic is linear. The first goal here is to find the minimum principle that is equivalent to Ax equal to B, and the minimization which is equivalent to Ax equal to lambda x. So I am not going till here. So I would just want to give you the idea that see these two ideas bring up, okay, they are dealt with Rayleigh coefficients. Okay, Rayleigh, L-E-I, okay, L-E-I, Rayleigh quotient. Okay, so quotient. So what is here that what is given here is that, so R of x Rayleigh coefficient quotient, that is R of x is x transpose Ax, that is my quadratic equation, divided by x transpose x. So here what is that? I am searching for the lambda value here. So what is that lambda that, okay, minimizes this R of x? So that lambda is the lambda 1. So I can just simply read out what is the Rayleigh quotient, Rayleigh principle. So Rayleigh principle says that the minimum value of the Rayleigh quotient is the smallest eigenvalue lambda 1, okay, into Rx, okay, reaches that minimum at the point, minimum at the first vector of x1 of A. So here, okay, when this will be minimum, tell me when this will be minimum. When this will be when here it will be lambda 1 and here it will be lambda 1. So then only this will be minimum. So he is telling that the minimum will happen at the ax, okay, ax1 is equal to lambda 1 into x1. So at this particular point the minimum will happen. So I'm not going to deal in detail this one. But just to, for the sake of completion, I am trying to introduce this Rayleigh quotient. We want to find the parabola that is p of x whose minimum occurs at x equal to b. So we can in algebraic way we can represent the parabola that is p of x. So the graph of p of x is half ax square minus bx. And now since this is a graph, now what I can do is that if I want to find the minimum value, I would differentiate. Because this is one variable. I would just there is no partial differentiation here. There is direct differentiation. So I would differentiate p with respect to x. That is dp by dx equal to this x square. This x square is 2x. 2 gets cancelled. Remaining is ax minus b equal to 0. So I get. Let me erase this. Okay. So I get ax minus b equal to 0, which implies x equal to a inverse b is the minimum point. So for this quadratic bowl, right, quadratic curve, x equal to a inverse b is the minimum point. So now what you do is that you substitute this x at this particular point. Okay, you substitute this in this equation and you would get the minimum point. So this point this point x equal to a inverse b will be the minimum if a is positive. Okay, the condition is this will be the minimum only when a is positive definite. The parabola opens upward like this, and to assure that minimum of p of x, not a maximum or a saddle, a should be positive definite. So why the whole idea of this lecture is to tell that if the matrix is positive definite, then minimum is guaranteed here. Coming to the next slide, right? If A is a symmetric positive definite, so I ensure that A is a positive definite, okay, so a symmetric positive definite matrix, then the quadratic curve reaches its minimum at the point x equal to b at the point. So if you substitute x equal to A inverse b in this, you would try to get this particular equation. Okay, so that's what it is shown here. The quadratic curve p of x equal to half ax square minus bx. So what you have to remember that in this case, this is capital A, because this is having only one equation. Okay, in this capital A is just A. Okay, capital A is scalar, it is not a vector in this case because it is having only one variable. So so if you try to substitute, so here x will be A inverse. Okay, x will be A inverse, that is, okay, A inverse is x equal to b by A here. Okay, x equal to b by A. In this, if you substitute here, then you would get this b square. Here also, this can be this small, the capital A will be small a. So this is the minimum point for this curve. And now let us take the curve, parabolic curve with respect to two variables, x1 and x2. The equation is given like this, and now you substitute x equal to A inverse b. Okay, x equal to A inverse b. Okay, A inverse b in this equation, you would get the minimum point at this. So this is a minimum point which is given through this equation. So now let us see one example. I have a quadratic equation. You can see x1 square, x1, x2. Okay, this is a quadratic equation with respect to two variables, x1 and x2. And now set the partial derivative to 0. So differentiate with respect to x1, keeping x2 as constant, and differentiate x2 with differentiate this function with respect to x2, keeping x1 as constant, and then you will get x equal to b. So now del p by del x1 equal to 2. I have differentiated this one and I got 2x1 minus x2 minus b equal to 0. Similarly, del p by del x2, I got this. And now I would try to represent in terms of x equal to b. So you can see that this is a, this is b, right? This is b, and sorry, this is sorry, this is yeah. These are the terms. These are the equations. So I am representing this equation in ax equal to b form, right? Ax equal to b form. I am just representing here. So these are x1. These are all coefficient. This is coefficient, and minus 1 is coefficient. You can see this is minus 1 is this coefficient, and x1 is the x1, x2 are the variables, and we got b1 and b2 on the right side. So now I got x equal to b, and I also know that with respect to two variables, the quadratic p of x is half x transpose ax minus x transpose b. And I also know that x equal to b gives the minimum point. That is x equal to a inverse b is the minimum. Now substitute x equal to a inverse b into p of x. Substitute this in this. Okay, substitute here. Substitute x equal to a inverse b in this particular equation, and you will see that you will get the minimum point. That is minus half b transpose a inverse b. You will get the minimum value. So now in many applications, you see that half x transpose ax is the internal energy, and minus x transpose b, that is the external work which has to be supplied, and the system goes to minimum point x equal to a inverse b, where total energy p of x is minimum. Okay, so now this slide is just to show you the pictorial representation of what is the meaning of positive definite. So positive definite means you will get a bowl shape like this, and negative definite means you will have maxima. This graph will be inverse. And now what is the meaning of indefinite? Indefinite means it will be like this, okay, like a saddle. And positive semi-definite means it will be like a valley here, and negative semi-definite means it will be inversed here. It is a valley in a inverse. It is in a reversed way. So this just to picturize what is the positive definite, positive negative definite, this is indefinite. Okay, all these things. And now let us see that given a graph x square plus y square. So this graph x square plus y square is a positive definite, and it is an upward parabola, and it has a minimum. Similarly, the other popular graph minus x square minus y square is a negative definite, because you can see minus minus here. Negative definite, it is downward parabola, and it has a maximum. And now x square minus y square is indefinite. It is a saddle, and it has neither minima nor maxima. So 2xy is indefinite, saddle, neither maxima and minima. Okay, so thank you very much. So these are some of the references which I have used in this for making my presentation. Thank you.